30. Turns out there are only 2 lectures to go in terms of the formal part of the thing. This one on binary rooted trees and Huffman codes, and next lecture on continuing Huffman codes. And after that, basically, we've got a week and a bit of revision. So I sent out an email this morning saying that your second test will be on Friday at 10 o'clock in the class. All being well, that'll be a quiz once I get everything set up. And I'll send out the last assignment, which you'll have basically till the end of next week. So we finished pretty well on time, with plenty of space to spare at the end to do revision, or spend, if you're comfortable in this subject, to revise your other subjects. Been a long semester. Right. So in this lecture, somebody's got a chat here. All right, so what's the deal with this test? How's it going to work? Is the exam changing? No, so I said that the exam would be a take-home exam. So that you'll be able to pick up the exam at any time during the exam period, and you essentially have 24 hours to complete it and get it back to me. So if you want to start your exam on the first day of the exam period, that's fine. If you want to leave it till the last day of the exam period, that's also fine, although I probably wouldn't recommend it. But you've got effectively 24 hours, 24-hour window at any time during the exam period. So basically, you email me, say you want to start the exam, and I'll send it to you. As far as the other assessment, you've already had one assignment which replaces the first test. So ordinarily we would have had 3 tests in class, but because of the shift to online teaching, I made the first test basically an assignment. The second test, well, the thing that will replace the second test is an online test that we'll just do, or you will do, next Friday at 10 o'clock. And if you've got a problem with Friday at 10, just let me know, and I'll see if we can organise something a bit different. So all being well, Friday at 10 o'clock, it'll be a quiz type test just online. So I think mostly multiple choice questions. There might be a couple where you have to do some calculations. And then the third test, we won't have a test. I'll revert back to an assignment style piece of assessment. So is everybody more or less happy with that test next Friday, 10 o'clock, unless you've got real problems coming along at 10 o'clock? Yep, a couple of thumbs up. As I said, if you do have a problem at 10 o'clock, that's fine. Let me know. We'll just organise another time for it. And then the third piece of assessment, I'll get that out to you, and you'll have basically till the end of next week to do that as well. Right. Let's get into Huffman codes. So let's see, I need to share a screen with you. Camera up. All right. So the basic idea in this, where we're going, is we want to construct what are called variable length codes. So remember the idea is that we've got some characters, let's say A, B, C, and D, that we want to send. And because we've got 4 here, now let's make it B. Because we've got 5 characters and we want to send it in terms of bits, 0s and 1s, we're going to code each character by a sequence of bits. Now, one possible way of doing this, since we've got 5, we're going to have to use, well, we can't use 2 bits, because if we use 2 bits, then we've only got 4 possibilities. So in fact, we're going to have to use 3 bits. So here are, oops, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So we might use 0 0 0 for A. We might use 0 1 0 for B, 0 1 1 for C, 1 0 1 for D, and 1 1 1 for E. So the idea is that if you want to send the word bad, then you would encode 0 1 0 0 0 0 .d 1 0 1, and you transmit that. And the person at the other end would receive this, divvy it up into 3 groups of 3, and then just read off 0 1 0 is B, 0 0 0 is A, and 1 0 1 is D. Now, what you notice is that this is certainly not variable length. All the letters get coded with exactly 3 bits, regardless of how common this is, how common each letter is. So the idea about variable length codes is that we're going to set up things so that more common letters or more common characters get coded with maybe 2 bits, but a less common character might get coded with 4 bits. And that poses a few problems. So that's where we're going. So just keep that in the back of your mind. The way we're going to, the method or the technique we're going to use is based on things called rooted trees. And the idea is, you know what a tree is. It's a graph that doesn't have any cycles. Okay, something like that. What we do with a rooted tree is we identify a particular vertex to be the root. So do it in red. So this is going to be the root vertex, and everything else comes off that. But we're going to add a little bit of an extra thing here. We're going to put things in layers. Okay. So the root vertex has 3, we'll call these children. Then that vertex has a couple of children, that has 1 child, and that has maybe 3 children. And this vertex doesn't have any, okay, maybe that has 2 children. This one has 1 child, that one doesn't have any. This has 2 children, that doesn't have any. And this has 3 children. Then maybe something like that. So a root vertex, so a tree structure with a distinguished vertex we call the root, and then everything follows down from it. We call these the descendants of the original root vertex, and at any level, these are the children of the things above. So these 2 are the children of the vertex above it. That's the child of the vertex above it. You could call them generations, generation 1, 2, 3, and 4. If you wanted to, you could think of these as a family tree. There's the matriarch of the family, her children, their children again, and their children. These things, let's see, these ones that don't have any descendants or don't have any children, they're called leaves. So a leaf is basically a child that does not have a descendant, or a child that doesn't have a vertex that has no children. So leaf, 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 leaf. Okay. Why are they called leaves? Well, because they're at the end of a tree. In particular, there are things called binary root trees. Let's get rid of something. Binary rooted tree. So the idea is, again, that you have a root vertex and we have generations or levels going down. But the difference here is that binary means that each vertex has at most two, so at most two children. So 1, 2. Often we call this the left child and the right child. Then this one might have only one child to the left, and this might have two children. Let's see. Okay, that might stop there, and then this might have two children, and that might have one child. And often we distinguish, not always, but often we distinguish between left and right children. So left child, right child. This has a left child but no right child. So these are the leaves. This has a right child, which in turn has a right child. You don't always have to distinguish, but we're going to do this distinguishing between left and right. And basically, what we're going to do is use this structure to construct a variable length code, which is a really neat idea. So the idea, continuing, the idea is that we're going to do lossless data compression. So with lossless data compression, you're going to take the original file, which is a whole lot of zeros and ones. We're going to compress it so it's smaller without losing any information, so that everything is fully recovered. So your information, your file, compress it, and then if you decompress it, you get exactly the same information back again. So something like a zip file does that. If you unzip a zip file, you get exactly the same thing back again. On the other hand, JPEG files, MP3 music files are not lossless. They actually lose information. So after you've compressed it, there's stuff that's been thrown away that you can never recover again. So starting with an MP3 file, you can't undo an MP3 file to get the original file back. It's called a lossy compression. Okay. ASCII codes. ASCII codes use 7 bits of zeros and ones for all of the alphanumeric characters. So the lowercase, the uppercase, the numeric characters 0 through 9, the characters like hashtag, @ $%, the punctuation signs like semicolon, slash, colon, quotes, and so on. Each of those characters in ASCII code get a sequence of 7 bit zeros and ones. So altogether, there are 128, 2 to the 7, 128 different characters you can code. So lowercase th and e correspond to the decimal numbers 116, 104, and 101. If you convert 116, it's 1, 2, 3, 4, 5, 6, 7. Okay, there's the binary number for 116. 111, 0, 1, 0, 0. The binary number for 104 is the next 7 bits, so 1, 2, 3, 4, 5, 6, 7. So that's 116, that's 104, and this is 101. So it's a fairly, if you like, primitive sort of code. So if somebody said, I'm sending you the ASCII code in binary form, and they sent you this, you'd look at the first 7 digits, decode it to 116 as a decimal number, and say that's T. Or you'd look at the next 7 bits, say that's H, the next 7 bits are E, and you'd know exactly what the message is. And I'm assuming here that there's been no corruption of the data as we go through. So these are not error correcting. They're certainly not error detecting. They're just a sequence of bits that represent the particular characters. And the important thing for us is that every character uses 7 bits. So it's a fixed length code. So if I've got a message that has 100 characters in it, how many bits do I have to send? Well, I've got to send 700 bits. And what we're aiming at is to try and reduce that. So we're aiming at variable length codes where some letters will end up having, or some characters will end up having only a couple of bits, whereas other characters might end up having 7, 8, or 9 bits. And that's really pretty amazing because, if I send you a message, let's see if I can just do something off the top of my head here. So if I send you a message that looks like this, we're about to do this, and I say that that's got 3 letters in it. Oh, you can't see it. If I send you this message, it's encoded, and I say it's got 3 characters, you've got to be able to figure out if it's a variable length code, where does one character end and where does the other character start? And it's not absolutely clear just at this stage, but it will be in a minute. So that's where we're going. Okay, let's have a look at an example that doesn't work of this variable length code. Code 2. We'll do code 1 in a minute. So code 2 is this. There are 4 characters, A, B, C, and D. Oh, let's do it this way. A, B, C, and D. Let's use just a single bit 0 for A. We'll use 1, 1 for B. We'll use 1, 1, 0 for C. And we'll use 1, 1, 1 for D. Now, the idea is that if I want to send the word bad, then what would I do? Well, B is 1, 1. A is 0, and D is 1, 1, 1. So I send that. And what does the person at the other end get? Well, they get 1, 1, 0, 1, 1, 1. And the person at the other end looks at this and says, oh, 1, 1, 0, that encodes C. And 1, 1, 1, that encodes D. So you sent me the message CD. Now, hang on a sec. No, I didn't send you the message CD. I sent BAD, not CD. So what's gone wrong? Well, we've used a variable length code. So each character has a code word that's of different lengths. So one has 1 bit, a couple have 3 bits. The real problem, of course, you've seen, is that 110 or 11 occurs in the beginning of C. In fact, if I send just 110, it's ambiguous. Did I mean BA or did I mean C? Now, because BA becomes 110 if I do it that way, but C becomes 110 if I do it that way. So clearly this isn't a very good code. It allows this ambiguity. And the problem here is precisely that. This code word for B appears at the beginning of other code words. And so what we want is a variable length code where that doesn't happen. So here's an example of a variable length code. So that's no good because of that thing. So what we'll do is a variable length code which doesn't have that problem. So again, just the 4 letters we want to send, but this time we'll encode A as 0, B as 10, C as 110, and D as 111. And now you look at this. Where's my green pen? That gets a good housekeeping tick of approval. No code word, so these are the code words, no code word appears as the beginning or the prefix to any other code word. So 0 is a single bit, no code starts with 0. 10, no code starts with 10. 110, no code starts with 110. So every code is unique as far as its beginning goes. So this is what we call a prefix code, and this one's not a prefix code. Okay, so basically this is good and that is not so good. And the advantage of this one is, suppose ahead of time you know that that your message has lots and lots and lots of A's in it. So suppose you want to send, the message A, B, A, C, A, D, A, C. Okay? Something which has lots of A's in it. How would you do it? Well, you'd send 0, 10, AC, 0, 110 is C. We're up to AA would be 0, 0. D is 111. AAAA is 0, 0, 0. And C is 1, 1, 0. You can see that this is actually not much longer than the original. I mean, it's bigger, but it's not much longer. If I had to use 4 bits for everything, 2 bits for everything, I'd have to have twice as many, or 3 bits for everything, I'd have to use 3 times as many. Now you can see the advantage of this prefix code, because if I receive this, it's pretty easy to decode it, because I just go along and say 0, do I recognize that? Yes, I do. That's A. So that's done. 1, do I recognize 1 anywhere? No, I don't have a 1. Is there a 10? Yes, there is. That's B. 0, do I have a 0? Yes, that's A. 1, do I have a 1 by itself? No. Do I have a 11 by itself? No. Do I have a 110 by itself? Yes, that's C. 0 by itself, yep, that's an A. 0 by itself, yes, that's another A. 1 by itself, no. 11 by itself, no. 111 by itself, yep, that's a D. 0 by itself, okay, that has to be an A. 0 by itself we know is an A, 0 by itself is an A. Notice that there's no 0, 0. That's because 0 doesn't occur at the beginning of anything else except for A. So 0, 0, 0, and 0, 0, 0 don't appear in here as codes. 1, okay, there's no 1. 1, 1, there's no 1, 1, but there is a 1, 1, 0. Where is it? C. So A, B, A, C, A, D, A, C. So encoded and decoded correctly. That's a really neat idea. I mean, this is really, really such a nice idea. So this goes, or is due to a fellow called Huffman, David Huffman. So it's called a Huffman code in his name. Let's see, he published it in 1952 while he was still a student, so he was only about 27. As a computer engineer, computers. So in the 1950s, they didn't talk about computer science, it was computer engineering. Most computer scientists actually had an electrical engineering degree. So how we do this, how we construct this, is to use the binary rooted tree. And basically, we're going to look at the proportions of each character. So here, A is predominant, so that will end up with a short code word compared to D, which isn't so predominant, which ends up with a long code word, relatively speaking. And what we effectively do is, my earphones just fell out, is we'll construct a binary rooted tree and the leaves will correspond. We'll construct a binary rooted tree and the leaves will correspond to the characters in the character set, and how you get to each leaf will correspond to our sequence of zeros and ones. So this will be encoded as 0, 0. This will be encoded as 1, 0, 0. This one will be encoded as 1, 0, 1, and so on. Okay, let's have a look at that then in detail. Paper. Right, suppose we've got the character set A, B, C, D, and E. And we look, so our message is just composed of A, B, C's, D's, and E's. Now, in practice, we're going to have a lot more characters. I mean, if it's text, we're going to have the 26 lowercase plus the 26 uppercase, plus the punctuation, plus all the ASCII characters. So 128 of them. For simplicity, let's just do this with 5 characters. Now, we look at our message and we count up the occurrence of A, how many times A occurs, B, C, D, and E. And we find that A occurs 25% of the time. And we find that B occurs 10% of the time. C occurs 18%. D occurs 7%. And E occurs 40%, a bit like English. Okay, so what we do is we rearrange these from least frequent to most frequent. So what's the least frequent? Okay, 7. D at 7%. Okay, what's the next most frequent? B at 10%. What's the next most frequent? C at 18%. A at 25%, and finally E at 40%. And now we're going to construct a binary rooted tree so that D, B, C, A, and D appear down at the roots. So at the moment, each of these are 5 individual little trees. Now I know that in the text, in the notes, it says there's no need to label the trees with their characters. So, but I have, because I find it actually easier to keep a track of things. Right. So what we do then is we take the 2 smallest ones, so in this case 7 and 10, and we combine them. Okay, so 7 plus 10 is 17, and that consists of D at 7% and a B worth 10. And we've got an 18, a 25, and a 40 left. They correspond to B, C. Oh, sorry, they correspond to C, A, and D. So that's step 1. Okay, left, right. We combine the 2 smallest again. So 17 and 18 are the 2 smallest. So we'll put those 2 together now. 17 plus 18 is how much? 34, 35. So there's a tree worth 35. This is this bit. This is that bit. So this is C, this is D, this is B. So we're combining DB there with C up to there. So this is still worth 7, 10, and 18. And now we've still got a 25% tree for A and a 40% for E. Now at this stage, you notice that 35 is bigger than 25 and smaller than 40. So what we'll in fact do is rearrange. So there's sort of 2 steps in this. We'll rearrange it so that the 25% for A is here, 35% for these is here, so that goes down to so that's D, B, and C, and then the 40% for E is there. Okay, once we've done that, we repeat the process again. What are the 2 smallest ones? 25 and 35. So 25 plus 35 is 60. So we now have a new tree worth 60. It's got 1 leaf out to the right for A. Then this bit, so there's a leaf down to here. Oh, sorry, connection down to here. And then from here, it's the same thing as this. So left, right for C. And from here, which is this, left to D, right to B. And we've still got 40% for E. Sorry. Did somebody chime in so they couldn't see it? Sorry. So we've taken the 2 smaller ones, combined them. Here's the tree for 35. Here's the tree for A at 25, and combined them into a single tree worth 60%. Now we've got 40 over here. So the next step is put these in order. So we've got 40 for E, 60 for everything else. So let's see. It's D. It's B. Those vertices back. Okay, and then we'll combine those two into the final tree, which looks like root vertex down to E, then down to this tree, which has a left child at A, and the right child splits off into the left and the right child at C, and then this child splits into D and B. So root vertex, and then all of these fit in different levels. So you can see here where the levels are coming in. One level, two levels, three levels, four levels. And we just make the convention that 0's on the right, left, 1's on the right. 0, 1, 0, 1, 0, 1. Okay, so what's our code? Our code now is, well, we've got A, B, C, D. So A, B, C, D, and D. Okay, well, what's the code for A? A is down here. So the code is going to be 1, 0. What's the code for B? B is going to be here. 1, 1, 0, 1. 1, 1, 0, 1. What's the code for C? 1, 1, 1. What's the code for D? D is here. 1, 1, 0, 0. And finally, what's the code for E? A single bit. Okay, now remember those percentages. E occurs 40% of the time. D occurs 7% of the time. C occurs 18% of the time. B occurs 10% of the time, and A occurs 25%. So these are percentage frequencies in our message. And you see straight away, E, which is by far and away the most common character in our message, only needs 1 bit each time. Whereas D, which only happens 1 in every 14 characters, needs 4 bits. B, which is only 1 in every 10 characters, also requires 4 bits. C, which is more common than A and D, but less common than E, gets 3 bits. So shorter than D and B, but longer than E. And then A, which is even more common than C, but still less common than E, only needs 2 bits. And as you go through, 0 is not at the front of any of these. 1, 0 is not at the front of anything. 1, 1, 1 is not at the front of anything. And 1, 1, 0, 0 is also not at the front of anything, nor is 1, 1, 0, 1. So now if I want to send the code bade, he bade him farewell. I say 1, 1, 0, 1 for B. A is 1, 0. D is 1, 1, 0, 0, and E is 0. And it's quite unambiguous because the person at the other end looks at this and says, oh, 1. Is there a single bit 1? No. Is there a 1, 1? Again, no. Is there a 1, 1, 0? No. There's a 1, 1, 0, 1, but that's not enough. Is there a 1, 1, 0, 1? Yes. So this will be my B. Is there a single bit 1? No. Is there a 2-bit 1, 0? Yep, there is. Is there a single bit 1? No. Is there a double bit 1, 1? No. Is there a 1, 1, 0? No. Is there a 1, 1, 0, 0? Yes. That's D. Is there a single bit B? Sorry, is there a single bit 0? Yep. So it's really neat. Now, of course, this is a very short message, so you don't see the compression involved, but if you have a message with, as I said, 40% ease, then 40% of the characters get represented just by the single bit 0. That's basically a Huffman code. We can then talk about the compression rate. So we've got 1, 2, 3, 4, 5. If we were going to use a fixed length code, we'd have to have at least 3 bits, because 2 to the 3 is 8, whereas 2 squared is 4. If we only use 2 bits, we could only have 4 characters. So since we've got 5, we need 3 bits. And there's a few combinations that don't correspond to a character. So if we were constrained to use 3 bits per character, and your message was 100 characters long, you'd need 300 bits. But if we've got 100 characters, and 25% are A's, 40% are E's, 10% are B's, 18 are C's, and 7 are D's, and we use the Huffman code, the E's, each one of the 40 is represented by 1 bit. The A's, each one of the A's, each of the 25 A's, would be represented by 2 bits, so that'd be 50 bits in the total. Each of the C's would be represented by 3 bits, which is 50-something, 54 in total. Each of the D's would require 4 bits. So 7 4s, 7 D's, 28 characters altogether, 28 bits altogether. And the B's, there are 10 of those. Each B is worth 4 bits. If we add it up, 212 bits. 212 is a lot better than 300. Now you can imagine doing this over not 100 characters, but over 1,000 or 1,000,000 or even 1 billion characters. So we've reduced the number of bits by how much? Well, 300 is what you need for a fixed length code. We've used 212, so we've reduced it by 88. 88 out of 300 is 29%. Remember, percent means divide by 100. So 29.3 divided by 100 is 88 over 300. So the compression rate is 29%. Actually, it's a little bit less, because what happens in practice is that if I want to send this message BADE, and I encode it like that, I actually have to put at the start the code book at the beginning of the message, and the code book actually will reflect which bit sequence corresponds to which character. So there's a way of doing that. So basically, you've got to send the dictionary, the code book, with the message. For a short message, the code book is likely to be as long as the message. But if this was, 1,000,000 characters long, then the code book is pretty short. If the message was 1 billion characters long, the code book is really very short in comparison, sort of adding very much. So in practice, the compression is actually a bit less, but this is a theoretical ideal. Right, that's basically it for Huffman codes. I reckon this is a really, really neat method. Next time, we'll continue this. Let me just stop sharing. Yep, so next time we'll continue this, and that'll be the last lecture, last official lecture, and basically we can concentrate on mopping up any of the problem sheets, or you asking any questions. We'll sort of treat them as tutorial type things. But don't forget, next Friday will be a test, and the final third assignment will be due towards at the end of next week, or maybe a bit longer if you want, but we'll aim for Friday next week. Okay, everybody more or less happy?
Yes, thank you.
Yep, good. So I said that I really like Huffman codes. I think that's just such an ingenious idea. Right, all being well then, when do we meet again? Thursday. So we'll treat Thursday as a tutorial session. You can ask questions, just drop in, maybe do a practice on the, look at the, so there are some old test twos. They'll be very similar questions to what will be on the quiz on Friday. Okay, so see you on Thursday then. And I'll finish up here.